Morning, AP Physics kids. I've been talking about this thing called a time constant, and I want to do a little formal discussion about that. Should be a pretty quick little video. But when we're talking about RC circuits, whether it's a nice simple one or like some of the more complex ones that we know that at the beginning we've got a battery epsilon, we've got the epsilon of our capacitor, and the capacitor's epsilon at t equals 0, epsilon c equals 0. And so this just acts as a zero resistive circuit, so current will start to flow. But over time, the epsilon c will increase, and so at t equals infinity, epsilon c equals the epsilon of the battery, and the current goes to 0. So here we'd have a current equal to epsilon battery divided by resistance. Here we'd have current equal to 0. And so what we want to talk about is kind of what happens in between now. And this idea of time constant is going to come up again. So let's look at the amount of charge that's built up on this circuit right there. So if I want to think about the amount of charge here, we had developed a charging equation. So we said the charge per unit time would be the epsilon of the battery, excuse me, times the, try that again, would be the epsilon of the battery times the capacitance value. So we got to give that some capacitance value. 1 minus e to the negative t over RC, like that. So what I'm going to do is I just want to make a little graph of what that charge on there would look like over time. So I'm going to make this be my charge. Here's my time like this. And we know at the very beginning, if my capacitor is initially discharged, it would be down here. And when this time gets really, really large, and that time gets to infinity, we'd have e to the negative infinity, which is 0, and so we'd end up just simply with epsilon b times c. So that means that this is going to approach this quantity, epsilon bc, like that. And so the shape that our graph will take looks something like that. So this is an asymptote. And that's why we've been using the idea of time of infinity. So it'll take an infinite amount of time to get there. Generally, though, we're not going to run our circuit for an infinite amount of time. We're going to run it for some finite time value. And so that's where this idea of time constant comes in. So I'm going to look at a specific time. So at t equals the quantity RC. So I'm going to take the resistance and the capacitance, multiply them times each other, I'm going to plug that into this expression. If I do that, I'm going to get my charge at RC is going to be epsilon times c times 1 minus e to the negative RC over RC. If I plug that into my calculator, what I get is Q of RC is equal to epsilon c times 1 minus, so now e to the negative 1. Sorry about all the moving around here. And so my Q at RC is equal to epsilon c times 1 minus, well, if I plug into my calculator here, let's see, e to the negative 1, I get the quantity about 0.36. If I subtract that from 1, I get 0.63. So what I find is that right here, sorry. Q of RC comes out to be epsilon c times 0.63. And so 0.63, we can think about that as 63%. So if we draw kind of a bigger version of our charge and time graph here, and we make this value up here be the quantity epsilon c, so that's the epsilon of the battery times the capacitance, so that's the maximum it could ever reach. We've got our asymptote here. We know it's going to go something like this. And so this quantity here, this is going to be the time equal to whatever the resistance times the capacitance is. If I go up to that spot and I go over, this now is equal to 0.63 or 63% of epsilon c. So if I do it again, if I double that time, so there's the time of RC, if I go out here to time of 2RC, go up like that, if I plug that into our equation up here, what I'm going to find is that I'm going to move up to 63% of that remaining 63%. So, 63% is not exactly 2/3. We'll say it's about 2/3. So we've gone up 2/3. We're going to go up another 2/3 to get to there. So if we go out one more time to t equals 3RC, we're going to go up here again. I'm running out of space in my graph, but I go to there. And so each individual time, we're going to move up another 2/3. So what engineers call this, and some physicists, but mostly engineers, they call this thing tau. So tau is what we're going to call our time constant. And tau is equal to the quantity R times C. So whatever the resistor is that's in line with our capacitor, we're going to call that the time constant. And what the time constant is going to tell us here is that after 3 or 4 tau, we can consider it to be fully charged. So what that means, we know that at one time constant, we're only at about 2/3 of the charge. After 2 time constants, we're getting closer, but we're still not quite fully charged. After 3 time constants, we're getting a lot closer. So we can never actually be fully charged unless we wait for an infinite amount of time, but we reach this kind of effective fully charged point. And so just like with a lot of things in physics, we're going to an ideal kind of value here. So it might be reasonable for you to say, for one person to say, you know what, I'm going to consider this fully charged after 3 time constants, because after 3 time constants, let's see, there would be 1 time constant, we'd have, let's see, about 1/3 of a third left, and now we'd have 1/3 of a third of a third left after 3, and after 4, we'd have 1/3 of a third of a third left. So it's getting to the point where it's not effective to let it charge for too much longer. So it's pretty reasonable to think after 3 or 4 time constants, we can consider it to be fully charged. So when we look at some sort of, circuit like this, and we know that this is going to end up having a final charge of epsilon d times the capacitance of it, like that, we can say that we're going to be pretty close to this when time equals 3 times RC, where that's R, or 4 RC. So not exact, but somewhere in that time period we consider to be fully charged. Not reasonable to say after 1 time constant. After 1 time constant is about 2/3 charge. So I hope that helps you when you're looking at your homework assignment. And when you see the term time constant, again, is typically using the variable tau, and that's going to be R times C. Have a great day, everybody. See you soon.